morning, this is Mr. Rivera. I am going to go over case study 4, shear vehicle modes. I find this to be very relevant to what we're looking today across the world. Japan, Venezuela, Colombia, fire barrel, a lot of that going on. So let's get straight into it. We're going to be learning how buildings vibrate and how problem solvers quantify this behavior using the four-story shear building model detailed in the problem statement. We're going to learn how to build massive stiffness matrices, solve the eigenvalue problem, compute the natural frequencies, interpret mode shapes, and finally what makes us stronger engineers. Okay. So part one, understanding the actual physical model. Let's imagine a four-story building during an earthquake. Each floor can move horizontally. Columns or walls resist this motion. Each floor is going to be modeled as a single lumped mass. And we're going to be making a matrix where each floor has a mass of 2,000 and floors do not affect each other's masses. The mass appears only on the diagonal. We're going to be capturing how the building's behavior aligns with our mathematics. Okay. I'm going to be diving into a little bit of the MATLAB code that will process these calculations and also link that to the physical model. So we're going to first start with the matrix that each floor has a mass of 2,000 units as detailed here. The mass matrix is going to be diagonal, meaning that mass is only the floor itself. It's going to be symmetric, and the problem statement detail that the same mass is used throughout all floors. So this equation that we write is mass equals 2,000 times I4, and here we have that diagonal matrix, right? The diagonal is a MATLAB function to get that end result in the matrix. So we're defining the part that revolves around building the actual stiffness matrix as detailed here in K. Important notes for students here would be the off-diagonal terms, the ones outside the diagonal, represent the connections between the floors. Negative values show the resisting forces between the adjacent floors, and the matrix is symmetrical because structural systems have this characteristic. So going into the actual eigenvalue process, we need to solve the K times X equals lambda times M times X, lambda being the eigenvalue, X being the eigenvector or the mode shape. Let's get to the rest of the MATLAB. We're going to be displaying the results. We're going to normalize the data and also scale this data. MATLAB scales this through the order of 1,000 as shown in this section of the code. So MATLAB is going to give us these values for the eigenvalues for lambda. Mode 1, mode 2, mode 3, and mode 4, and the natural frequencies by mode with the same alignment 1, 4, 3, and 2. Going into the natural frequencies, we need to undergo the square root of lambda, and it's going to give us this result detailed here. Okay, so let's go into interpreting the physical modes. The calculation of the physical modes gives us a floor with a negative 0.9 value, second floor with 1, third floor with a negative 0.9, and finally fourth floor with 0.64. So this details that floor 1 is moving left, floor 2 is moving right, floor 3 is moving left, and floor 4 is moving right, but to a lesser degree than floor 2. Right, 64 is less than 1. So we have two nodes that we could call inflection points between floors 1 and 2. There's a change, and floors 3 and 4, there's a change given the slopes. So these are the locations where the motion is going to change direction. We can also say that floor 2 has the largest displacement, it's the biggest magnitude, dominates this mode. And the physical meaning for this would be that this mode represents a swaying pattern, alternating floor motions, basically. Going into mode 3 as an example, I'm going to show a little bit of floor there. So going into mode 3 using the previous learning, the positive is right, that negative is left. This mode shows perfect antisymmetric bending. So we're going to have floor 1 right, floor 3 left. However, floor 2 and floor 4 essentially have zero motions. Use detail as magnitude, zero motion. We can characterize this curve as an S curve. We're going to have positive displacement at the bottom. We're going to have a negative displacement at mid-height and zero displacement up top of your body. This is considered a very stiff constraint mode. Going into the bonus, mode 4. Mode 4 here, we can interpret it as floors 1 and 3 are moving together. Floors 1, 2, 3 move left. 1, 2, 3 left. And floor 2 moving much more. Much more. This form chart sorry guys, I lost track here a bit with my analysis, so getting back into it. Floors 1, 2, and 3 move left, right, as detailed by the negative, and floor 2 is moving much more, given the magnitude it's pulling on the side. That's detailed. This mode, I would say, the top floor here moves the opposite direction. Floor 4 moving to the right, forming a very sharp bend at the top. And we can explain this physical meaning as this being the highest frequency mode that represents deformation in a specific place, particularly the top of the building. This is important for, we would say, we're going to load the rooftop with heavy equipment, the stability of a parapet for maintenance, and accelerations transmitted by those roof-mounted devices are going to impact this system. Now, if we were to summarize the entirety of the system here, mode 1 was discredited given the mathematical nature of the results. We only have the realistic mode 2, 3, and 4s. Here is a quick overlay of all the plots. We discredited mode 1, but also portrayed here for full transparency. So mode 2, if we were to detail how each of these modes, how they move, and what are the meanings of these movements, we can start with mode 2 and how it moves. It's going to have alternating floor directions with the meaning that it's going to be it's going to show a sort of a S-wave like bending with amplification of characteristics of mid-floor of the building. Mode 3 would be perfect asymmetry between the two nodes, detailing a key meaning here for high frequency shear mode. And finally, mode 4, how it moves is going to be lower floors moving together, roof reversing, right, top floor reversing. And this is key meaning for this is a high frequency mode. Sorry, that is going to be affecting the very top floor of the building. Now, why does this makes us better engineers? It allows us to understand the characteristics of a particular system and how the real world interacts with them. We get to understand also implications of doing changes to the structure and accounting for the external stimuli on it. And that is it. That is it for my share of case study forward. Thank you.